Gentlemen, I don't see any lady here. We would like, I'm happy to start our next session, and we have substitution for our previous invited speaker. Such situation happened, and our colleague, Professor Linas Svilainis, will present his topic related with time of flight topic. Okay, the floor is yours.
Thank you. Hello everyone. I think we hear quite frequently that somebody is measuring the time delay. So my presentation is about time delay estimation techniques, but not in general, but in ultrasound. Although the techniques, they are more or less applicable into other areas, but our expertise comes from ultrasonic measurements. And when it comes to time of flight, so maybe for those who are from different fields, what is time of flight? So ultrasonic imaging or measurement usually is done in such way that you have the excitation, and usually the ultrasonic transducer impedance is high, so usually the excitation voltage is high, so high voltage signal is produced for probing, and then this signal travels into an ultrasonic transducer and then into test media. And if there are some defects or inhomogeneities, or we just want to measure how long for the signal it took to propagate through the media, signal is received back. Sometimes the same ultrasonic transducer is used for reception. Sometimes different ultrasonic transducer is used for reception. Then, of course, it is low signal, so it goes to some amplifier. Usually it is low noise preamplifier that comes first. And then, of course, you have the reflected or traveled through signal that you need to estimate how much was the delay. And usually it is called time of flight or time delay estimation. And it seems first application is like radar. Then when you send the signal, you get the reflection and you know the distance to the obstacle. But actually there are many more applications. First of all, it is imaging, that is defect location and sizing. Thickness measurement, when you measure the thickness of the material. But there are even more interesting applications. For instance, you can measure the load. And for instance, there was a project with the Bosch. When they assembled the car, they want to use a lot of bolts, but every bolt has to be as small as possible because the total weight of the car is finally huge. What is usually done, that there is a wrench which has a limitation in the torque, and once the torque is limited, so you are no longer tightening the bolt. But if you send the ultrasound along that bolt and measure the time of propagation within the bolt, then you are able to estimate what is the load in the bolt, and bolt can be made even lighter because then it is true estimation of the load, not through the torque, but through the tension that comes into bolt. You can measure the material density. For instance, there is an insulation material and you need to estimate the density of the material, so you just send the signal through the material, and because the ultrasound propagation velocity is dependent on the density of the material and the elastic constants of the material, then you can measure both the elastic constants and the density of the material. And of course, in all scientific technical measurements, for instance, this is the sonar that is used for probing to get the distance to the clouds, but not using the radar technology, but ultrasound. Because the mechanical properties depend on temperature, so ultrasound can also be used for non-invasive and very fast temperature measurement. For instance, if you use usual sensor, so it takes minutes for the temperature to settle down. Remember how long you have to keep the thermometer in your armpit. But with ultrasound, it is just immediate, and there are many applications like flame. You have a flame, and you want to measure what is the temperature distribution within the flame. So you take a lot of ultrasonic rays, And by measuring the time of flight of these rays, you are able to estimate the temperature distribution within the flame. So there are no technologies to do this otherwise. And of course, it is used in chemical industry, for instance, curing processing. Curing process when you are putting the, for instance, epoxy, you are putting the base material and the hardener, and you need to establish when the material has cured. Why this is important? Because in industry they want to empty the mold as fast as possible. But once they don't know when the material has cured, so they need to estimate it somehow. Usually it is done with the trials. Then when they open the mold, they see that material has not been cured, so they have to throw it away and do the new mold. But with ultrasound you can measure that online. Also, there is another application like curding in cheese production. I don't know whether there are countries where you produce the cheese. So in cheese production it is really special. They need specialists, because the curding is when you put some acid into milk and milk starts curding, and you need to estimate the cutting time, when to cut the curds to make the cheese from that. With ultrasound it is easy because you can estimate from the velocity or time of flight. Of course, navigation and robotics, Alberto has presented today that they are used in car parking, but in robot navigation, in underwater navigation, all the submarines or sea ships, they would not be able to see beneath what is happening in the water if it is not the ultrasound and if it is not the time of flight estimation. And of course, for trilateration, it is essential. And of course, in medicine, not just in the sense of imaging, when you send the ultrasound and you are trying to get the image of the ultrasound, but also, for instance, blood diagnostics, when you need to establish how fast your blood is coagulating, because some illnesses, they have certain delay in coagulation. So ultrasound can be used for glucose level measurement, for tissue estimation, for cancer diagnostics, because the ultrasound is able to measure the elastic constants of the material. So this is the way what is done in elastography. Elastography is the way to produce the image, which is not the internal image of the human organs, the human tissue, but it is the image of elasticity of this tissue. And doctors, they already know that beyond certain level of elasticity, there is a possibility that it is a cancer. And of course, ultrasound is not X-rays. It is not dangerous for the human health. Of course, you should not go beyond certain mechanical index, the intensity, but as long as you keep the mechanical index beyond the standard level, so it is not dangerous both for the examiner and for the patient. And in food industry, sugar content measurement, fruit ripeness, meat or milk products, quality monitoring, and so on and so on. When it comes to time of flight estimation, there are several techniques, and the most simple one is the amplitude, when you just measure what is the amplitude of the signal that has been traveled, and because you know that spherical front is squared, and of course if you know that there is also the amount of the attenuation, then you can measure that. But this technique is not that accurate. Then the other one is to measure the phase when you use the sinusoid, and you compare the phase of the sinusoid that has been transmitted and the sinusoid that has been received. Of course, in such case, there is a problem that if you go beyond 360 degrees, so there is an uncertainty whether it is one period or two periods of the sinusoid. So this technique has this problem, but the advantage is that it has high energy because the signal is continuous wave. Of course, there is a solution to use two frequencies. If you transmit one frequency, another frequency, and you measure the phase difference between those two frequencies, then you are getting rid of this uncertainty in which period you use. Then another way to measure the delay is to use frequency modulated signal. And you see this one was constant frequency, and for this one you can see that the frequency, for instance, is increasing constantly. So with this constantly increasing frequency, you are able to estimate the delay by measuring the instant frequency difference between the transmitted and received signal. And of course, the last one, which is most popular nowadays, it is group delay or pulsed measurement technique, when you are not using the continuous wave signal, but you are using pulsed signal, the signal that is relatively short. At the very beginning, it was indeed pulse signal, as you can see here. So usually it was really short, but with the time being, new signals have been implemented for the measurement. But basically, those are three techniques that can be done for the time delay estimation. And of course, when we are trying to estimate the delay, we can divide into two techniques in a way how the delay estimation is done. The first one is the local properties match, when we are selecting just one instant in a signal, and then by matching this signal, this instant in a signal with transmitted and received, we measure the time delay. Or we can use the global properties match, that is, the whole signal is used for delay estimation. So first, simple one, local properties used for time delay estimation. For instance, you have received the signal, so where is the arrival time? So some might say that the arrival time is here, somewhere at the beginning, but you have to admit that it is hidden in the noise. So usually it is better to use the highest amplitude, so usually it is the peak location that is used for time delay estimation. But the problem to do this in analog way is that there is no analog technique to detect the peak. But there is a simple approach that you take the derivative, and after you take the derivative, then it is the zero crossing. And zero crossing is simple comparator that you can use. Of course, if it is digital, then you need to interpolate between those measurements somehow. Then this means that you need to measure several values around the peak. Another approach, still local properties, and it used to be almost 90%, but with the years running, everybody are discovering that these techniques are not optimal. So nowadays I could say that it is just 50% of techniques used are using local properties evaluation, and with the time running, with time of flight cameras appearing, this percentage is dropping down significantly. So the other approach is just to use some crossing, some level crossing, not the peak, but some level crossing. But the problem then is that this time delay estimate is dependent on the amplitude of the signal. This can be overridden either by automated gain control or by using two level crossings, one before the peak and another beyond the peak, and then taking the average. So in such case, more or less, this bias or systematic error is reduced. Or you can go again to zero crossing, the same as we have discussed with peak location when you take the derivative, or just pure zero crossing. But the problem with zero crossing is that you need to know when to take this zero crossing, because you see there are several zero crossings, 1, 2, 3, and if there is a noise, so there are many zero crossings. So usually it is combined. Then first we take certain level crossing to know that signal is actually has already arrived, and only after that we take the zero crossing. Zero crossing is prone to certain errors, but at least one error dependence on the amplitude of the signal is avoided. And of course you can use two zeros and then combine those two. But the problem with all these techniques is that not all signal is explored, because once you are taking the zero crossing, or you are taking the peak position, or you are taking threshold at some level, only this tiny piece of the signal defines what is the quality of your measurement. But actually, if you have a signal which maybe here is short, but as I told you, there are signals which are much longer, this signal energy is much larger than the energy if you are taking just this tiny piece of the signal for evaluation. That's why these global properties matching techniques are getting more and more popular. And one of the best known techniques is the correlation. So how the correlation works? You are looking for likelihood function. Likelihood is how similar two signals are. If you know what was the shape of the signal transmitted, and once it is you who know what signal was transmitted, because it is you who transmitted the signal. So once you know what type of the signal was transmitted, then you are looking for the correlation. And correlation actually is matched filter. And you know that the narrower is the filter that you use, the better is the signal to noise ratio. And if you are using the optimal filter is the one that is matching the magnitude response of the signal. So what else can be matched? Because we have made the shape of the filter ideal, and the shape of the filter matches the shape of the signal spectrum. It is the phase. So if the phase for the optimal filter is, we do not care. With the matched filter, we do the phase to be opposite of the signal phase. And if we do this, this is equivalent to have the complex signal and complex conjugate. So you know that if you multiply the complex signal and complex conjugate, you are getting rid of the imaginary part, and actually you are getting the magnitude of the signal. So this is the idea behind the matched filtering. So actually it is the cross correlation. And once we do the cross correlation, you see the result is somewhat different. But the essence here is that now the peak contains all the energy of the signal, because correlation is the multiplication. You multiply, you shift, multiply, shift. So if you have matched the signal and the copy of the transmitted signal, so they match, so the signal squared actually, and signal squared and summation is the energy. So what you have at the peak here, actually at the any point, but the peak is the best signal to noise ratio, you have all the signal energy. Which means that if the signal was long, so you have squeezed all the energy into one point. And this means that you have very large signal energy, so the noise goes down, because noise is not correlated with your signal. Unless you use the signal which is noise-like, and it is exactly the same noise that is generated now. Because some signals are also noise-like, but noise, it never repeats. So even if you use noise type signal, it will be not correlated. And then you find the location of the cross correlation function B. Then of course everything is done in digital domain. So again you have samples which do not match with the peak. Peak is somewhere between the samples. Then you do the interpolation, and ideal interpolation according to the Nyquist sampling criteria would be sinc function, but usually some truncated functions are used, like parabola, for instance. Once you find the peak, then this is your estimate of the time delay. Another technique which is not that widely used, and the reason is very simple. Cross correlation is easy to calculate, because in order to get the cross correlation, you just transform both signals into frequency domain, take the complex conjugate of the reference signal, multiply and go back into a time domain, and you have the response. But there are techniques which are called difference minimization, and these are performing more or less the same, because they are starting with the signal which was transmitted, and then they analyze the signal that has been received. But instead of multiplying, which is the base for the correlation, the reference signal is subtracted from the received one. You have to admit that once we take the difference after subtraction, the remainder of the subtraction, only when the transmitted signal matches the signal where we actually receive the signal, only then the remainder will be minimal. And there are two techniques to calculate this remainder. It is L1 norm, that is, you take the remainder and take the modulus of that, and then sum or integrate as in analog case, or L2 norm, that is, you take the energy of the remainder. In both cases, this is the comparison of correlation. You can see correlation is giving you the peak here. but L1 norm and L2 norm is giving the minimum here. The example presented here is when both the reference signal and received signal are the same amplitude, but if the signals are different amplitudes, so of course minima will not go down to 0, but to a certain level, but anyway, it will be minimum. It might look that the minimization techniques, they are not advantageous compared to the correlation technique, but when it comes to super resolution, they have very large advantage. And this advantage is not seen here, but you need to divide 1 by L1 norm of the remainder or L2 norm of the remainder. Then you will see that if it was 0, for instance, in this case, it will go to infinity. This means that the peak, now you have peak because before it was minima, but if you take 1 over the remainder, then the peak will be really sharp. And these techniques are addressed as super resolution technique. The only disadvantage is that the calculation takes much more time. And of course, interpolation is somewhat different. If in case of correlation, so it is parabolic or cosine interpolation that is used. So here is for L1 norm, it is triangular function that performs the best, and parabolic function for L2 norm. And there are some exotic techniques. Authors are trying to apply them, and they report certain success, but they are quite complicated. They are detached from the physical meaning of what is done, but they are worth of mentioning here. It is establishing different likelihood criteria apart from correlation and minimization. For instance, you calculate the minimum of the entropy. Entropy is the measure of how many different values the signal has. If it is noise, then it has all the different values, because noise is going to all the amplitudes you can imagine. But if it is the signal, it is more or less defined. Then for the signal, the amount of the values taken, it is much less. This means that once you minimize the entropy, then you can say that where the entropy is minimal is the arrival time. Good thing is that in the previous examples, in correlation and minimization techniques, you need reference signal. That is, you need to know the signal that you have transmitted. And you might say, what's the problem? I know the signal, how it is transmitted. No, you need the signal that has been passed through the transducer in transmission and passed to the transducer in the reception. And usually it is not that easy to take the signal. Of course, there are techniques, and once we're working long time in the field, we know how to do that. But this technique has an advantage. It does not require the reference signal. You just calculate the entropy and that's it. And of course, some quasi-likelihood criteria. These are a few references to have a look at. When it comes to measurement, some basics, that when it comes to accuracy or decreasing the uncertainty, we have two types of errors. We have random errors, which are defined by precision term, and bias errors, which are defined by trueness term. When it comes to random errors, it is Cramer and Rao, those are two scientists from 50s, 60s, which have discovered this simple relationship. It is Cramer Rao lower error bound. That is, this bound tells us what is the minimum random error that we can achieve if we use the signal that is using the matched filtering, because matched filtering is exploring all the signal energy. If you use any other technique, it will be not the case. And as you see, the equation is quite simple, because this is the effective bandwidth of the signal. More or less, you can say how much of the bandwidth signal is covering, and this is the signal energy, and this is the noise power spectral density. So all these, they can be estimated forward before your experiment starts. So using this equation, you can predict what will happen with your signal once you use the correlation or minimization techniques for time of flight estimation. Just to give you more feeling of what is this effective signal bandwidth, actually effective signal bandwidth can be thought of center, but actually it is center of gravity. of the spectrum of the signal, so more or less it is center frequency of the signal, and the envelope bandwidth, more or less it is the bandwidth of the signal. And you can see that these guys, they are squared, which means that as soon as envelope bandwidth gets 3 times less the center frequency, it is not important anymore, or at least it is not giving any significant advantage. And then it is F0 or center frequency that defines the achievable accuracy. And of course, once we know those two, we can go into further analysis. So when it is noise power spectral density, of course it is mainly prevailed by analog noise, but of course the quantization noise prevails if you haven't selected the amount of AD converter bits, and jitter noise, it is the noise of your oscillator, that is how tight is the frequency stability of your oscillator. And of course, when we apply this Cramer Rao lower error bound, you can see that usually when you do the experiments, there is a region where you have very nice fit with Cramer Rao, then there is a certain level where you are deviating from that because of the quantization noise, but if you are putting quantization noise, so you can see that approximation also works. And of course, when you are going into a very high noise level, then you are approaching Zivzarkaya and Barankin regions where this dependency is not that easy. But of course, also there are equations that define how errors can be predicted. What to tell is that if we are using simple pulse signals, there is a contradiction between two requirements, because if we want bandwidth, then we need to make the signal as short as possible, because the shorter is the pulse, the wider is the bandwidth. But then if we reduce the duration of the pulse, then the energy of the pulse is also decreasing. And because those two guys, they stand here, so with pulse signals, you cannot get any further, because you reduce the duration, you reduce the energy. That's why there was a need to search for other types of the signals, and the new type of the signal that was proposed is the spread spectrum signal. I cannot tell who proposed that first, because radars, they are using this, and since long time in ultrasound, spread spectrum signals in industry was implemented just recently, and just the coded excitation in medicine, in non-destructive testing, in industrial tests. Still, there are no standards, so it is still not used. But more or less, what are the advantages? The spread spectrum signals, they can be long, but their bandwidth does not relate to the energy. This means that you can make the signal longer, this way increasing the energy, but you still maintain the bandwidth, that is, you maintain the resolution, and of course you maintain the accuracy. But the punishment is the side lobes. If, for instance, we take the pulse signal, so you can see the pulse signal, if you take the envelope, does not have the side lobes. But if you take, for instance, this is chip signal, you can see that those signals, they do have the side lobes. And of course, the pulse, you see, pulse does not have the side lobes, even if you take the correlation function of the pulse. So sometimes not correlation, but miscorrelation or mismatched filters are used. So those are special filters that distort the reference signal somehow, or the excitation signal is distorted in the way that the side lobes are reduced. This is just one more explanation what are spread spectrum signals. This is the spectrogram. Horizontal axis is the time, vertical axis is frequency. So if you take pulse signal, you can see that for pulse signal, all the frequency components, they appear the same time. That is, they are put on the top of each other. What is wrong with such approach? The problem is that you need very high resolution AD converter, because your signal is concentrated in one place, so you need, I don't know, 14, 20 bits, depending on the frequency range, AD converter in order to cope with the range. Otherwise, you will be introducing quantization errors. With tone burst signal, this is not the case because you see with the tone bursts, all the energy is spread over the time, but this energy is concentrated just in one frequency. So if we want the resolution, it is not suitable for us. So the spread spectrum signals are something in between the video pulse and radio pulse, because you see they are at some angle. This is just one example. It is a chirp or linear frequency modulation signal. Other signals, they drop the frequency components in a various fashion, in time domain, in frequency domain. But more or less, this explains the idea beyond the spread spectrum signal. Our group also proposed APWP signals, which are binary excitation. And with this binary excitation, it is easy to design the electronics because excitation electronics is simple. And because of these IPVP properties, they are also spread spectrum signals, but they are easy to excite. And their side lobes or spectral properties, they can be programmed. This is the demonstration how it is optimized. So you see we start from such signal, but later we optimize the side lobes. This is APWP signals. And then, of course, we are avoiding Barankin or Zip-Zarkavi regions because those regions, they are coming earlier if there are side lobes. And then when it comes to bias errors, because the previous discussion was on the random errors, when it comes to bias errors, first of all, one of the sources is this interpolation, because ideal function for interpolation would be sync function. But if you want it faster, because usually in industrial equipment nobody has time, so they want to do it as simple as possible. So usually the interpolation is done over those points that are at the maximum. And you can see what are the interpolation errors. So the worst performance is for parabolic interpolation. You can see this is matching. You see there is the reflection is coming exactly on the sampling grid. So of course it is natural that there are no sampling errors. But the further we deviate, and you see in the center when we have half of the sampling, errors negate again because there is in the middle. So in the middle, both errors coming from the left sample and the right sample, they negate each other. But in the middle, you see we have significant errors. And for parabolic interpolation, it is those errors, they are huge. When it comes to L1 norm interpolation, you can see linear interpolation or triangle interpolation. It is also causing the errors. And there are two techniques like cosine interpolation and frequency domain interpolation. Frequency domain interpolation is virtually free from interpolation errors. Those are the equations for interpolation, and those are demonstration what is the influence of the interpolation on the errors. You can see that they are suddenly increasing. We have derived the practical equations when you can calculate what are those errors. So you can see that the same parameters, sampling frequency and envelope bandwidth is used, and center frequency and envelope bandwidth is used. So you can estimate what is the size of the error, or even you can calculate what should be the sampling frequency to avoid the errors or to keep them below a certain point. These were matched with Cramer Rao errors. When it comes to another source of bias errors, it is the case when we have multiple reflections that are spaced close to each other. And what we have discovered that if two reflections come close to each other, then there is also the bias error caused by this neighboring reflection. This is the case, for instance, you have a step and you have two reflections. And this is the experiment that has been done. You can see that the position in time, despite it has been compensated. You see the distance between the signals, we have subtracted that. These are just errors remaining. So for the first and second reflection, you see they are opposite, which means that the errors, once you take the difference between two signals, will be even larger because they are taking the opposite sign. From the signal processing point of view, it is easy to explain because signal, pulse signal, any signal that we are using, we want to be it wideband. So this means that it has multiple frequency components. And once those frequency components, they come into phase, then there is no influence. You can see that there are places where this error is 0. But once you sum two sinusoids with different phase, you have the sinusoid with a new phase, and none of the measurements is satisfied, and you have errors in both cases. What to do? We have tried several techniques, and we have found out that iterative deconvolution somewhat reduces the errors, but then we have realized that there is another technique. It is reiterative deconvolution. This is the algorithm how reiterative deconvolution works. If iterative deconvolution is working very simple way, you have a signal, you have train of the reflections, you have this reference signal, and you are trying to find the largest reflection. Once you have found it, you subtract it, and then the rest of the reflections are revealed. And then you found the next largest reflection, you subtract it, next largest, you subtract it, and so on. I don't know, maybe not iterative deconvolution, but matching pursuit, orthogonal matching pursuit, basis pursuit. So more or less all these techniques are talking about the same. But reiterative deconvolution working is a bit different, because once you got all the signals subtracted, you already know the positions, which signals to subtract. You go back again to the raw signal, which is without the subtraction, and you subtract all the signals except the signal that you are interested in. This means that you are removing this bias error from the neighboring signals, and then you estimate the position of this signal alone. And you do that with every signal. Of course, that does not come from the first reiteration. You need approximately 5, maximum 10 reiterations in order to get rid of those bias errors completely, but more or less those bias errors can be removed. And you can see, for instance, here you see there was an error in estimation, but when we got after few reiterations, the position of the signal has been estimated properly. Of course, then another essential problem is the reference signal, how to produce the reference signal. So there are certain techniques, and one of the techniques which was proposed by Dangirutis and Sani is model based. So this one, which was proposed by Sani, is when you have Gaussian envelope and sinusoid inside, so it is Gabor function. But nowadays, plenty of functions proposed to do so-called blind deconvolution. When you don't need the reference signal, you are just making the reference signal yourself. And to conclude, you now already know, those who were not aware, that both the signal amplitude, phase, or frequency modulation, or group delay can be used for time-of-flight estimation. And there are 3 likelihood criteria that are most common. So the most common is the maximum of the cross-correlation function, and there are 2 minimization criteria: minimum of difference of magnitude or square, and high-order statistics. And then the reference signal, you can pre-record this reference signal somehow, or you just create this signal synthetically somehow, making some Gabor function or other functions. And of course, when it comes to synthetic signal, you can apply the adaptive filtering, because then you can change the shape of the signal easily. When it comes to errors, there are 2 types of errors: random errors and bias errors. So first of all, electronics noise defines the amount of random errors, and then sampling jitter, quantization, and of course the signal energy, which is essential, and the effective bandwidth. When it comes to bias errors, they are caused by interpolation, caused by neighboring reflections, and of course deviations of the reference signal, because reference signal, when the signal that you have transmitted, when it travels in the test material, it is affected by dispersion in frequency domain, and dispersion goes not just in amplitudes of the signal, which can be easily compensated, but in phase. This means that the further the signal travels, the more it is distorted, and these distortions, they are also causing bias errors. And we have also tried adaptive deconvolution, when you change this reference signal according to the losses, and of course this compensates for bias errors that are used. And of course spectral aliasing, when you have multiple reflections, alias them on top of each other. And To tell you more, the amount of errors can be predicted because there are papers that are dealing with the analysis of those errors. They can be predicted, and the parameters that are used, they are quite simple, like center frequency, envelope bandwidth, energy, noise, that's it. And of course, you need to select carefully the reference signal in order to get rid of the errors mentioned. Thank you for your attention.
Any questions, please? No questions? We fit in time. Thank you, Linas.
Thank you.
So now it's time for lunch. Lunch will be served in the building A, in front of the building. You'll find it. Okay, thank you.